Welcome, my dear warriors. Welcome, welcome, welcome. Yes, 8 o'clock, 12th syllabus. And all the JEE 2026 students are welcome out here for the next amazing class of your current electricity. And we are going to do Kirchhoff's two laws, current law, voltage law, their applications, then the questions on symmetry and also Wheatstone's bridge. And then we will also see some cool RC circuits, resistors and capacitors, all of them together. In today's live class with you, your Capto, your Captain Shreyas on the number one JEE English channel, which is Vedantu JEE English. If you have not yet subscribed, be a member. Hi Nikita, welcome. Hi Robu. Hi Akhil. Hi Maidhan. Welcome, my dear lovely warriors. And in the previous session, we have already done, where is it? By the way, 11th standard topic, we just did vertical motion under gravity. And then we did combination of resistors, combination of cells and capacitors also in the previous class. So please have a look at it. Those are amazing, important lectures. Okay. And yeah, before that we did current density, drift voltage, everything. That's the 100th like, guys. You should be doing that. PDFs are there in the comment section. Thank you so much, Darun, God of Physics, Shreyas Sir. Next lecture today. Yeah, I hope you are here, Prajit. Either live recorded. When will you explain problems of capacitors? Today, man. Today, Abhiram. Revision, hey, yeah, detailed. Hey, revision, no, bro. Full on detailed. Homework, 5 home. Oh my God, one person solved the homework. What are rest of the guys doing? Not interested in getting into IIT or what? Okay, welcome, Jayashree. Hi, Prakash. Welcome, everyone. So let's start one by one. But before that, remember, if you want my complete guidance and the best teachers in pure English, we have a JEE 2026 batch with the entire syllabus of 11th and 12th PCM being covered, along with mains plus advance, with the material, with everything that you need, test series, assignments, DPP, study material, everything is there in the Sigma batch. That is the batch which every student is, enrolling into if you are serious, if you are only serious about JEE 2026. Okay, so the link for joining the Sigma batch is down there in the description box of every video. You can definitely check it out. Yeah, the Sigma batch for 2026, and there are two versions. One is the prime version and one is the combo version, where you get hard copy of the modules and the revision flashcards which can fit inside your pocket, so you don't have to make notes. The batch is just starting 21st July, so you better hurry up, right? So let's begin with a lecture, and let's start with Kirchhoff's current law, and then we will go to Kirchhoff's voltage law. Okay, so starting off with current law, the Kirchhoff's current law is based on the conservation of charge, is based on the conservation, on the conservation of charges. Charge is conserved, it cannot be newly created, or existing can't be destroyed. So if you take a junction, what is a junction, sir? Wherever the wires are joined together, they are meeting. Meeting place is a junction or a node. Okay. Hi Dhanush, welcome. Jaya. Yep. Nice to see new students also joining to the channel. Okay. Hello. And make sure you are watching every class live or at least recorded. So when you have a node or a junction, some currents might be entering in, some currents might be exiting out. So if you sum up the total, this is the summation, symbol for summation. If you sum up the total current coming in, then it will be exactly equal to the sum of the currents which are exiting out. That is what it is. Okay, total current entering in is exactly equal to the total current exiting out. Now, if you go with this particular diagram over here, as you can see in this particular example, okay, current 1, current 2, current 3 is coming up in. So I1, I2 and I3 is going in. So if I add them up, should be equal to, I can say I4 and I5 going out should be equal to I4 plus I5. That's how it works. That's how it works. A lot of other examples are there. Sometimes in, JEE, they have asked these kind of nice questions like this. Okay, something like this maybe. And then they give things like, this is 1 ampere bro, this is, let's say, 2 amperes, let's say this is 7 amperes, Let's say this is 3 amperes. Let's say this is 2 amperes. This is I. Let's say this is 8 amperes. Chumma have put up some values. Question is, can you find the value of I? Can you find the value of I? Okay. So a lot of other diagrams also can be drawn. Okay. So this is just one variety. Okay. Kinematics, but I'm not. Okay. Nikita, I'll just come back to you. Okay. Sarana, welcome. Yes, our book solutions. I'm very good and nice to see you over here. Welcome. Yeah, I think long time back you used to come. Where were you all these days? Okay. So over here, as I can see, I need to figure out how much current is there in this branch. For that, I need this branch. For that, I need this branch. For that, I need this branch. So 2 amperes is going in, 1 ampere is going out. So if 2 is entering, 1 is going out, there is a deficit of 1 ampere. So more 1 ampere should go out from this junction. Make sense? If 2 is going in, 2 should go out. So 1 is going here, the remaining 1 ampere will go over here. Now, if you look at the next junction, 7 amperes is going out, 1 ampere is coming in. So there is a deficit of 6 amperes. So that 6 amperes should go in like this. Does that make sense to you, my dear warriors? Because 6 and 1 will together make 7. You need to see the balance, the remainder. So 7 is going out, 1 is coming in. So more 6 should go in to make up 7. Conservation of charge. Now look at this node over here. 3 is going in. From this junction, 6 is coming out. For this junction, 6 is going in, but for that same current, this junction, it is going out. So 3 and 3 make up a 6. So this should be 3 amperes. So 3 and 3 together will give out 6 amperes. Now you go to this junction. 8 is coming in, 3 is going out. So the balance of 5 amperes should also go out from this particular junction. Everyone till this point? Okay. Now this 5 and this 2 at this junction are entering in. Together they will add up to give you how much, my dear warriors? Obviously, they will give up 7 amperes. So 7 amperes is the answer. Hi, Dhanu, welcome. Okay. Yes, I'm lucky that you remember. Okay, welcome. No problem. Yes, be in any batch, you are a Vedantu student. That's important. I'm so glad, Jagan. Yeah. So kinematics, but I'm not able to do the problems, PYQs. Okay, Nikita, that's a very specific question. How about you putting it up as a comment or probably pinging me on Telegram or Instagram, Captain Shreyas? Maybe I can help you out with that. Okay, Telegram, Instagram, or comment. I will just answer that, Nikita. Great. Hi, Jai. Hi, Vijima. Welcome, 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 welcome. Okay. Everybody clear till Kirchhoff's current law, how it works? Give me a thumbs up, smash the like button. If you've forgotten, please smash that like button right away, right now. Okay. All right. Now, let us go to the next concept, which is basically Kirchhoff's voltage law. Now, this particular law is based, this is based on conservation of energy. Conservation of energy. Conservation of energy. Number one. Number two, it is not applied at a loop like this particular thing. Sorry, it was not applied for a node. Like Kirchhoff's current law is applied on a node or a junction. Kirchhoff's voltage law, it is applied on a loop, on a loop or a closed circuit, or a closed circuit, or a closed circuit. Like if I start from here, I come back to the same point. If I start, let's say here, I should go around and come back at the same point. You take any complex path, but you should come back at the same point. That's how you apply KVL. KCL is at a junction. KVL is for a complete loop. Okay, complete closed loop. Okay, so in such a situation, what happens is, if you add up all the voltage differences, in that particular closed loop, the answer will always be a big fat 0. So that is Kirchhoff's voltage law. It kind of makes sense because if I start from here, I increase 5 volts, 2 volts, 3 volts, 5 volts, something. But if I come back, the net change in the voltage should be 0. Makes sense. So Say for example, I'm going across a path. I have 2 volts of increase across some device, another -4, then -3, then +1. So what extra voltage should be there so that it becomes 0? +2 -4 is -2, -2 -3 -5, -5 plus 1 is -4. So +4 will make it 0. So this is how it works. But now I am pretty sure you are wondering, sir, wait a minute, this +2 -4 -3, how the hell did you get these numbers and how do I apply this? Please show it practically. Don't just show like this. Obviously, man, I'm going to show it. But this is the law. This is the formula. Now let's see how do we exactly use it. That is the most important and confusing part. See, let me tell you. If you talk about a resistor, then we say that the voltage drop across the resistor using Ohm's law is IR. When I say V is IR, please understand it is always the voltage drop which is IR. But what do I exactly mean by it? See, always the current across a resistor goes from high potential to low potential. So if this is 7 volts, this will be 2 volts. If this is 10 volts, this might be 3 volts. So high to low. So there is a difference of voltage between the two ends of a resistor, which is IR. So because the current in the resistor goes from high to low voltage, it kind of makes sense that as I am moving, I am crawling across the circuit, when I encounter a resistor, if I'm going in the direction of the current, then I'm going from high to low. That means I'm dropping the voltage. But as I crawl, if I go against the direction of the current, while I'm crawling in that circuit, because I have to go across a closed path, if I'm going against the direction of current, then I'm going from low to high. Against the direction of current, low to high, that means it is a jump. So if I go like this, it is an increase of plus IR. But if I go like this, then it is negative IR. That's all. Keep this in mind. Okay? Very straightforward. I will apply it on a circuit and show it to you. But for now, remember the sign convention. Similarly, if I have a capacitor like this, maybe this is the positive terminal, this is the negative terminal, this is C, this is plus Q, this is negative Q. Obviously, this is again high voltage, this is again low voltage. So, what is the formula for voltage across a capacitor? Remember, charge is equal to capacitance into the voltage. This V stands for actually the voltage difference. Keep that in mind. Even in Ohm's law, that voltage V actually is voltage difference. So a lot of students get confused at times. It is difference of the voltage. Symbol used is V. Actually, it should have been delta V. Anyways, because I'm going from high to low, positive to negative. So when I go from here to here, voltage will be Q by C. So negative Q by C. That is the change, because high to low, it is negative. If I go from negative to positive, I'm climbing up. So there is a jump of the voltage. Voltage will be charged by C. So it will be plus Q divided by C. That is how you apply it for capacitors. And lastly, the only element left is a battery. So if you have a cell like this, left side is high, right side is low. Same thing I'm using everywhere. High, low, high, low, high, low. This is EMF E. Then a battery always creates a potential difference of E. So therefore, if I am going from the negative to the positive terminal, that is like this, it will be plus E. And if I'm going from high to low, positive to negative terminal, I'm climbing down. So that will be negative E. E being the EMF. That's it. There is no formula here. Direct EMF is the voltage difference. Now, how to use it? That's what I'm going to show you on the next slide. Say, for example, we take a circuit like this. There is a resistor, maybe a branching over here, some battery over here, another resistor over here, some branches over here, and this goes like this. Maybe there is a capacitor over here. This is positive, this is negative. Let's say this is R2, this is, let's say, E1. Let's say this is R1. Some branches over here, another capacitor. Maybe this is negative, this is positive. Let's say this is C2. Okay, let's say this is C1. Chumma, I'm taking something and all, guys. Okay, another resistor, let's say R3 over here, and another battery over here, E2, and something like this, maybe. Uh, okay, and another capacitor, let's say C3. This is plus, this is minus. Okay, and okay, this is another battery over here. Let's say this is E3, and okay, that's about it. So let me also assume some currents, maybe current I1 going like this, maybe this current is, let's say, I2 going like this, maybe some current going here, no resistors, so no point. Here, maybe some current is going like this, which is I3. Some currents might be going here and there in these branches. So I'm just assuming some currents over here in every single branch. Okay, anything can go in, anything can come out. Chumma, I'm taking up something. Okay, now this is my circuit, and let's say I want to apply Kirchhoff's law over here. So first decide my path. Okay, decide the path which you are going to take. So I decide the path. It is going to be, let's say, like this. Maybe I'm going to start off with here. I'm going to go like this. I'm going to go like this. I'm going to go like this, like this, like this, and I'm going to come back. This is the path which I have chosen. Step 1 clear? You choose a path. Yeah, it's Kirchhoff's voltage rule, Dhanushri. KVL, Kirchhoff's voltage law, which is based on conservation of energy. So when you come back to the same point, there is no net change in the voltage. All the positives will be balanced by negatives. The positives and negatives are decided by how you are traveling across EMF, capacitor, and resistor by these three rules or sign convention. So let's apply, then you will understand. See, I start from here, this particular point. Do not forget that point, or else you will be like, sir, I am going again and again. I forgot where I started. Don't do that. Okay. Anyways, starting off with the first thing over here, as you can see, I encounter a resistor and I'm going in the direction of the current. Look at it. In the direction of the current, you drop. Current always goes from high to low. So that means what should come first? It should be negative current in that and resistance in that minus IR. That is the voltage change in that device. Then I get into a battery. I'm going from positive to negative. Positive to negative, it's a downgrade, degrade. So how much degrade is it? It is negative, basically even, positive to negative. Again, I encounter a resistor. For resistor, the formula is IR. So current into resistance, I2 into R2. Okay, so minus I2 into R2. Why minus? Because I'm going from high to low, and in the direction of the current, always the voltage will drop. In the direction of the current, the voltage will drop. Okay, fair enough. Then I go and I see a capacitor. From positive to negative, look at it. For a capacitor, positive to negative, obviously high to low, it's a degrade, negative Q by C. So I should put over here negative. Here maybe the charge is Q1 divided by nothing but C1. Q1 by C1. Everybody fine till this point? Okay. So next, what is there? You get a battery over here, which is E3. I'm going from negative to positive terminal. Negative to positive. Increase, upgrade it is. So give plus sign over here. So plus, what is it? E3 over here. Everyone fine till this point? Okay. Next, coming back, negative to positive in a capacitor. Negative to positive. It is an upgrade. So plus Q3 by C3. Okay. And then I go to a battery. Battery negative to positive. It's an upgrade of how much? E2. Upgrade of E2. Resistor, but I'm going against the current. So whenever you are against, it's positive. So plus I3 R3 plus I3 R3. So be always careful about resistors. Capacitors and batteries are usually easy. It's only the resistor. In the flow of the current, voltage drops. Against the flow, voltage increases. So that's why positive. I'm going like this. Lastly, I get a capacitor positive to negative. So it's a degrade. So minus Q2 by C2. And then finally, I come back to the same point. When I land at the same point, I will put 0 over here. That's it. That's the answer. Is that clear? I'm so thankful. Thank you so much for appreciation. And you will find all my lectures over here on the English channel out here. And very simple English I use, very easy to understand. Any Hindi medium, Marathi medium, Tamil medium, anybody can understand. So it's very laddu English. It's not like some hi-fi English we use. Okay, because the idea is to give you quality education, and many people are in English medium these days. That's why we have created this channel. Okay, fine, sir. I understood. Sir, give me one more example, sir. Okay, I'll give you one more example. And sometimes you might be asked a slightly different question just based on the sign convention. That is this part. So look at this particular question. Okay, so imagine they tell you this is nothing but plus 10 volts, and there is a current of 2 amperes which is going through a resistor of 4 ohm, and then there is also this particular battery which is connected, which is of 5 volts, and there is a branching which is happening here, and maybe more 3 amperes of current is coming like this, and there is another resistor of 2 ohms which is going over here. Sorry, 1 second. There is a branching happening like this. 1 ampere 5 amperes current is going like this, and then there is a resistor here of let's say 2 ohms. The question is, can you find the voltage or potential of this particular point? That is the kind of question which can be asked, which is a slightly trickier question. And let's see, how do we solve this? It's not that difficult. We have to just use the sign convention. This is for everyone, dropper, fresher, everyone. This is for 2026 students, right? So 12th standard syllabus. So any person who has a 12th standard necessity, okay, whether it is a backlog or you want to learn it from the scratch, these lectures are right from zero, ground level. All right. Now, first thing that I realize is if I need the voltage at this point, I somehow need to figure out the current here, maybe the voltage at this point, because current into resistance gives me voltage drop and all of that. So to find the voltage here, maybe I need the voltages here somehow. But first thing I realize that I need the current for sure. So as you can see at this particular junction, 2 amperes is entering in, 5 amperes is exiting out. Can you guys quickly guess and tell me how much current will be going in or out? 2 is coming in, 5 is going out. How come more is going out? So obviously to balance it out, yes, the remainder 3, the balance, the deficit is 3 amperes. So 3 amperes should definitely be going in. And this is purely justified by Kirchhoff's current law, KCL, right? So 2 amperes plus 3 amperes is equal to 5 amperes. Whatever is coming in is going out. That's all I have applied. Everyone till this point absolutely clear? Okay. And I'm so glad that you have watched my previous lectures from previous years, but please do watch the live classes. The fun in live is completely different. I'm pretty sure old classes are also nice, but the live fun is completely different. Now observe, guys, from here to here when I'm traveling, I'm encountering some things, either an increase or decrease of voltages. If I somehow add them up, I might get how much ever potential is left. It's like saying, sir, I have potential of 100 now. Sir, you are taking away 2 from me. You are giving me 5. You are taking 7. You are giving me 10. So if I add them up, whatever is the balance will be the voltage at the other point. It's like you have some money in the bank account, you're withdrawing something, you're giving something, you're depositing something. So how much is left? That is what this is all about. So at this point, I have 10 volts. As I travel, I encounter a resistor. It is going in the direction of the current. So I'm traveling in the direction of the current. So there will be a drop. How much? Minus IR. I into R. So there is a drop of the voltage. This is what I had initially. I encounter a battery. I'm going from negative to positive. So I'm climbing up in voltage. So it should be plus 5. There is an upgrade. There is an increase. There is an increase. Perfect. Now, as I go here, I'm going against the direction of the current. So there should be an increase in the voltage against the current in the resistor. It is an increase. I is 3, R is 2. So this is what I had. This is what I take, I give, I take, I give. Whatever is remaining is the voltage V. Do you guys understand this equation, how I wrote it? Okay, so it is nothing but my initial voltage plus whatever drops or increase I am getting will be the final voltage on the other side. That's all. And here I'm just using this sign convention which I've just given it to you over. So what is this? Which I've given it to you over here. So this is a very important chart, huh? Yeah. All right. Amazing. Amazing. Now, what is the answer then? What is the answer, my dear students? Let's see whether you can figure it out. So 10, therefore 10 minus 8 plus 5 plus 6 is V. Therefore, V is equal to 10 minus 8 is 2, 2 plus 5 is 7, 7 plus 6 is 13. So 13 volts is the correct answer. The potential at this point is 13 volts. Got it? How many of you loved the question? How many of you enjoyed the question? How many of you understood a different kind of KVL question now? Yeah? Lovely. So let's start applying into more questions coming up on your screen. Okay? The current through the 5 ohm resistor. So this is the MCQ. Let's see if you can start applying it. Current through the 5 ohm resistor is asked. Let's start by assuming some currents. Maybe some current will go like this. At this junction, it will probably split like this. And some current might go like this. It might even split over here. And it might again come back. But this is ground. It just means that it is 0 volts. That's all. And it is going like this. Fair enough. So maybe the current over here is I1. The current over here is I2. Okay, this is I1. And maybe this is I3 kind of current. This symbol just means this point is 0 volts, nothing else. This point is 0 volts. That's what it means. Now comes my next step. I've assumed the currents. No harm in assuming. I will apply Kirchhoff's law. Which loop should I take? I have multiple choices. Now, as I can see, the best choice will be to go like this and come back over here because I need this I2. So it is asked, why will I travel here? Asked is here, why will I go here? Doesn't make sense, right? So I will go across that resistor and see what happens. Let's say I start from here. I'm encountering a battery. I'm going from the negative to positive. So I'm jumping up, upgrade, plus 6. I'm going in the direction of the current. So it will be a drop of IR. So minus I2 multiplied by 5. I'm going in the battery from negative to positive. So it's an upgrade of plus 8, which is the EMF. And I'm returning back to the same point. So 0. Is that making sense, everyone? Perfect. Yeah. Great. Now, what is this? This I2 into 5, I can take it on the other side. 8 plus 6. 8 plus 6 is here. And we have 5 times of I2. 8 plus 6 is nothing but 14 is equal to 5 times of I2. Therefore, I2 is 14 by 5, or I2 is how much, guys? Come on. I2 is how much? Yeah, it will be slightly more than, yeah, it will be slightly more than how much? It will be slightly more than 2 point something, but I don't see any option over here. Maybe they have messed with the calculations. Yeah, it should have been ideally 2.8 amperes, but I think they have messed it up for some reason. Why have they messed it up? Why have they given 0.4? Yeah, see why they have given the wrong answer, because they have messed up the terminals. They have messed up the terminals in the diagram. So actually it was like this, but in our question, this was negative, that was positive. So in the answer slide, I think they have messed it up. So none of the options are matching. So maybe I can just make up some answer over here just for satisfying our MCQ, right? So maybe I can make this as 2.8 amperes. Now it makes sense. Yeah. Perfect. Cool. So they have messed up with the terminals out, or else for this particular diagram, this is the answer. If you change the terminal here, obviously, then the answer will be completely different. So our answer is 2.8. Okay. So no point keeping these slides. I'll just delete it so that now we can proceed ahead. Okay. Moving ahead to the next question. The diagram shows a part of the circuit, the potentials at A, B, C are 30, 12 and 2. The current through 20 ohm resistance is. Current through 20 ohm resistance is. There are multiple ways of doing it. I will show you one way and the other way both. So as you can see over here, 30 to 12, 30 to 2, I can take two paths. So starting off by taking this particular path over here, I will start by going like this and reach over here and see what is the equation I can write. Initial voltage is 30. I am going through the resistor in the direction of the current. So there will be a drop of I into R. I am going in the resistor in the direction of the current. So again, I multiplied by R. And finally, I end up at this point, which is having a voltage of 12. So initial voltage plus the changes will be the final voltage. Remember, I'm not going across a loop, but I'm going from a point to another point. You can still apply Kirchhoff's concepts of increase and decreasing of voltages. So anyways, if you take 12 over here, so this will be 30 minus 12 is nothing but 10 I1 plus 20 times of I2, because if these two go on the other side, they will become positive. So it will become 28 is equal to 10 times I1 plus 20 times of I2. So this is, let's say, equation number 1. Now what I do is I take some other path. Maybe I will go like this from here to here and then see what do I exactly get. Starting, I'm getting 30. From here to here, again a drop of minus 10 times of I1. From here to here, again a drop of minus what is it? I3 times of 20. And finally, I'm landing here where the potential is 2 volts. So 30 minus 2 is 10 times of I1, 10 times of I1 plus 20 times of I3. Okay, 30 minus 2 is basically, sorry guys, while doing this, I made a small mistake. 30 minus 12 should have been 18. I don't know why I wrote 28. This was 28. Yeah, this is 28. Okay, is nothing but 10 times of I1 plus 20 times of I3. This is my second equation, but I am not very satisfied with this because I have 1, 2 and 3, I1, I2 and I3, three variables, and I will only get two equations, which is not solvable only mathematically. Yeah, that is the problem. Okay, so what do we do now? What do we do now? I have an idea. If you apply Kirchhoff's current law at this particular junction, if you apply Kirchhoff's current law at this junction, I1 will be nothing but I2 plus I3. I1 will be nothing but I2 plus I3. And what if you look over here and see already 10 I1 is here also, 10 I1 is here also. What if I subtract the two? Maybe I will have equation with only I2 and I3 and then I can solve it. Now I had three equations, three unknowns. Yes, perfect, solvable. So solving these equations, I'll get current 1, current 2, current 3. And you know, that's a task, but still manageable. It's not that difficult also. Okay. So if you want, you can substitute over here only. As you can see, I3 will be I1 minus I2. I3 will be I1 minus I2. So substitute it here only, this particular I3. So let's see what do we get. You will get basically 28 is equal to 10 times of I1 plus 20 I3. I3 is I1 minus I2. I1 minus I2 over here. So this will be 10 I1 plus 20 I1 minus 20 I2. So 10 plus 20 I1 is 30. So that will be 30 times of I1 and this will be nothing but 28. So now this I can call it equation number 2, and now you can solve this because this is I1 I2, this is also I1 I2. Now this is solvable. In fact, you can just add both of them and easily you will get I1. From I1 you can get I2 and then you can also get I3. Is that absolutely clear how to solve these equations? Yeah. So solving this, you can definitely get I1, I2, I3. But do you see the length of the question? It's quite lengthy. Isn't it quite lengthy? So solving these three equations, definitely you will get it. Okay. Simple technique is first equation and second equation. If you add, immediately 20 I2 and 20 I2 will get cancelled. But I don't like this method because it's little lengthy. Instead, I have another suggestion from my side. How about assuming this point's voltage to be X just for this problem? I'll assume the voltages and I will apply voltage difference is IR for every resistor. That makes kind of more sense to me. This is 30, this is X, this is X, this is 12, this is X, this is, what is it? 2. So, voltage difference for the 10 ohm resistors, if I apply which formula? I'm using voltage difference is current multiplied by resistance. So, the voltage difference over here is 30 minus X is I into R, that means I1 multiplied by 10. Same way over here, I can say X minus 12 is I2 multiplied by 20 and X minus 2 is nothing but, what is X minus 2 guys? It is I3 multiplied by, what is that? 30. Now we all know I1, I2, I3 from here, and we also know using Kirchhoff's current law, yes, I1 is I2 plus I3. So I1 is 30 minus X divided by 10. I2 is nothing but X minus 12 divided by 20. I3 is X minus 2 divided by 30. 0, 0, 0 cancels. So we have 1, 2 and 3 over here. So multiply everything with 6. So it will become 6 multiplied by 30 minus X is 6 by 2 is 3. So 3 into X minus 12. 6 by 3 is 2. So 2 multiplied by X minus 2. Solve this further guys. See what is that you get. So this will be 180 minus 6x is equal to 3x minus 12 3s are 36 plus 2x minus 2 2s are basically 4. From this you will get the value of x and then you can find out everything. Come on, what is the value of x that you are getting? Quickly tell me in the chat box. Everyone, what is that value of x that you are getting? Let me know guys in the chat box. Minus 36 minus 4 is minus 40. Minus 40 goes on this side. It will become 220 is equal to 3x plus 2x is 5x. 5x plus 6x is 11x. So therefore x is 20 volts. Just check this out. X is 20 volts. Sir, but x was not asked. Why did you do this? Hold on, bro. X was not asked. But what was asked? Current through 20 ohm. Current through 20 ohm. That means I2 was asked, no? So I2 I know from here. So use this equation. X is nothing but 20. So 20 minus 12 is I2 multiplied by 20. So therefore I2 will be 20 minus 12 is 8 divided by 20, which is divisible by 4, which is 2 divisible by 4, which is 5. So it will be 0.4 amperes, which is basically your option number A then. Yeah, everybody with me on this? Yep, option A is the right answer. Correct, Gokul, everyone. Loved it. This is how you can solve it using this method. This method was slightly better. See, it is Kirchhoff's law only at the end of the day, but the way we are approaching is slightly different. I'm again using voltage differences. At the end of the day, Kirchhoff's law, voltage law, uses the concept of voltage differences, but the manner in which I've used it is slightly different. I've also used Kirchhoff's current law. This method, which I used, was slightly a lengthier method. So it depends from problem to problem. Like in this particular question, it was easier to solve it using Kirchhoff's law. It was easier to solve it using Kirchhoff's law, KVL. But some problems it might not be easy. So it depends from question to question. Let's take up another question over here. Find the current in each branch of the circuit. Wow, this is a good question. This is just to make you understand and apply Kirchhoff's law again and again little bit better. So it's a complex circuit. It is neither series nor parallel. We have no other option but to apply Kirchhoff's law. Okay, definitely I'll put up the plan. Yep, no worries. I'll definitely put up the plan. Okay, so no other option but to start assuming the currents one by one. So let us say some current is going over here like this. Let me call that current as I1. Okay, and let us just say some current is going over here like this. Let's say I call it I2. Okay, now what will happen is these both currents will add up together over here, I1 and I2, and this current will be obviously I1 plus I2. Yeah, kind of makes sense over here. And similarly, let's assume some current over here. Let's assume it as I3. That same current will come here. So from this branch, two currents are going out, I2 here, I3 here. So obviously the current which is going here will be this and this together, which will be I2 plus I3 like this. So that same current is going here also, I2 plus I3. Okay, fair enough. These are the currents going in every single branch. Everything I know now. Okay, now once I know this, then I can start writing down the equations one by one. I can start writing down the equations one by one. So let's start with this circuit first, this loop first. Kirchhoff's voltage law, let me apply. So if I apply it for this loop starting from A, how will it look like? Starting only, I'm going in the direction of the current. So there is a drop of minus current, which is I1 plus I2 into the resistance, which is basically 6. Then again current into resistance in the same direction. So minus I1 multiplied by R1. Remember, this current is still going to be I1. This is also I1. Here I encounter a battery. So there is a sudden jump of plus 21. I'm going in the direction of the current. So there is a drop. So minus 5 times of I1. I land at the same point. So it should be 0. If you want, you can simplify this. Nothing wrong in that. So minus 6 times of I1 minus 6 times of I2 minus I1 minus 5I1 minus 5I1 plus 21 is equal to 0. So 6 and 1 is 7. 7 and 5 is 12. So minus 12I1. Okay. So therefore, 21 is 12 times of I1, and this I2 will go on this side. So 6 times of I2. So this is equation number 1. Just check this out. So 6 plus 1 is 7. 7 plus 5 is 12. So 12 I1 will go on the other side as positive 12 I1. Minus 6 will become plus 6. 21 will stay as 21. So that is for this part. Same thing you can apply it for this part of the circuit also. Again, if you apply, what will it look like? Let's say I start from point A only. So minus I1 plus I2 multiplied by 6. This branch I2 plus I3. So minus I2 plus I3 multiplied by 8. Okay, battery of plus 5, negative to positive. In the direction of the current, it drops. So minus I2 multiplied by 4 is equal to 0. Again, just open up the brackets a little. Minus 6 I1 minus 6 I2 minus 8 times of I2 minus 8 times of I3 plus 5 minus 4 I2 is equal to 0. So what will happen? Just keep that number 5 over here. I1 6 times, nowhere else is there. So it will become plus 6 I1 on the other side. Minus 6 I2 minus 8 I2 is 14 I2. 14 and 4 is 18. So plus 18 times of I2, and I3 will become plus 8 times of I3. This is equation 2. Same thing you do it for the third loop and then solve it. You're getting the point, right? Yeah, this is how we apply Kirchhoff's law. I can see 3 variables, I1, I2 and I3. So I will need those 3 equations. Without that, I cannot solve them. Yeah, definitely this is useful for everyone. Yeah. Meter bridge, we are coming to it. Okay, so if you start maybe from point B over here, first thing you encounter is this resistance. So minus I, which is I3 multiplied by 16, increase of plus 2. So plus 2 over here, and here a drop of nothing but minus I2 plus I3, I2 plus I3 into basically 8. This will be 0 when I come back to point B. So what is this? Minus 16 times of I3 plus 2 minus 8 I2 minus 8 times of I3 is 0. So therefore, just see 2 will be equal to, this will be just 8 times of I2, 16 and 8, 16 I3 and 8 I3 will make it 24. So plus 24 I3. This is equation number 3. So we got 3 equations, solve them in your own leisure time. I just wanted to show you how to apply Kirchhoff's law. Solving them, you will get the answers. Okay, I have put the answers on the next slide, but you can definitely solve it as homework. So please take it up as homework to solve them. Solve 1, 2, and 3 as homework, and then figure out how much is I1, I2, and I3. Once you get I1, I2, I3, everything you can mark it in the currents. Cool, guys. Understood how to apply Kirchhoff's law? Can we go ahead? Tell me quickly in the chat box. Okay, perfect. Now let's go to a very unique kind of question, which is called symmetrical circuit. Symmetrical circuit plays an important role. Many times there is some kind of symmetry, and then you can solve the problem easily. So imagine you have to find equivalent resistance or capacitance between 2 points, and these are the 2 points. These are the 2 points between which you want to find the resistance or capacitance. Some kind of symmetry could be there. I don't know. Maybe Chuma, I'm drawing something and all. Okay. Some kind of symmetry could be there. Maybe this is what it is. Some kind of symmetry. Whatever is there on the left is there on the right. Here also maybe I just again Chuma show some kind of symmetry. Okay. Some kind of symmetry is there between the points where you want to find the resistance. As you can see in both the questions, there is a line of symmetry. This is the line of symmetry. Here also, whatever is there on the left side is there on the right side. First, identify if the problem is actually based on symmetry. Usually, nobody will tell you, hey, listen, this is symmetry problem. You, by the look of it only, can see, oh, left and right, up and down are same. Then, first, identify that. The line of symmetry must be, first of all, perpendicular to the points where you are trying to find the potential difference. This is the most important criteria. The line of symmetry must be perpendicular to the points across which you are finding the resistance or capacitance. That is the most important criteria. Okay, so let me just mark that over here first. So line, that particular line of symmetry should be perpendicular to the points across which the equivalent resistance or capacitance is to be found. Once that is done, what you can do, see if there are some components on that line of symmetry. As you can very easily see over here, that yes, I can see one component here and some another resistor or capacitor or whatever is there over here. It could be a wire, resistor, anything. Here, I do not see any component on the line of symmetry. Instead, I see a junction. So here there are some kind of components, either resistor, capacitor, or maybe a wire. Here, what we have is a junction. Whenever you get any components, basically ignore it or basically remove them. What will you do? These components, completely remove them. Remove them, get rid of them. If you see a junction, then split it along the line of symmetry, along the line of symmetry, along the line of symmetry. What do I exactly mean by that? Observe carefully. Along this line of symmetry, first of all, I can already see that there are two components. So what I will do, second, little difficult. This component and this component, right? I'll just get rid of them. That's it. See this. Along this line, this and this were the components. Just get rid of them. There is no use of them in the circuit. Now it looks like a much easier circuit. Now this is nothing but a simpler, maybe series or parallel circuit. This is a simpler series or parallel circuit. These two are in series, these two are in series, these two are in series, they are in parallel. Now it is solvable. What about here? What did I mention? I said split it along the line of symmetry. Yeah, just split it along the line of symmetry, meaning you do this. Let me show it here. Split it along the line of symmetry like this. So one part is here, one part is here. I'm splitting that junction along that line of symmetry. Did you guys just get it? So this junction, you just split it along the line of symmetry. The moment you see this, now these two are in series, these two are in series, they three are in parallel. I mean, it's simple question now. So this is a simpler series and parallel circuit. So there is no wire in between of them. Please understand that. So there is no wire in between of them now anymore. So you can now very easily solve this. Got it, my dear warriors, how to solve these kind of questions. Now, why does this exactly happen is because on that line of symmetry, because that is equidistant from left or right or positive negative terminal, all the points on the line of symmetry are at the same potential. So all points on the line of symmetry are going to be at the same potential, are at the same potential. And whenever the potentials are same, just think about it. If this point and this point are at the same potential, then if this is V1 volts, this is also V1 volts, then this thing in between becomes completely useless. This thing in between becomes completely useless. So V1, 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 5 volts, 5 volts, 5 volts. If all of them are at 5 volts, what is this device or this device doing? There is no voltage drop across it. So it will not store any charge. There will be no current flowing in it. So it's completely useless. Okay. So there will be no current flowing in that particular part. So that's why this part and this part are useless. So that's the reason why we remove it. In this scenario, because there was no real device, so I just elongated, I just split it like that. So anyways, the upper part and the lower part will be anyways separate. I mean, there will be no interaction between these two because current can't flow in this particular direction. Current can't flow in that symmetrical line direction. Okay, because there is no absolute voltage difference. Okay, I hope this is clear, everyone. Yes, Adarsh, you are going to get my recorded VBuddy classes as a repository in the Sigma batch. The entire VBuddy lectures are going to be made available. Entire syllabus is being taught, and I am coming there every now and then to make you solve problems, to make you understand different things. But remember, also PNJ sir is there along with me to teach you most of the physics. So together we are teaching the physics, but you also have, same Diksha ma'am, Namrata ma'am, all of them are there in the batch along with other teachers too. Cool. And How do you manage time for school going itself? Because that's a common question which I get. But I will tell you, try your best to keep your school attendance as low as possible. Try not to get yourself involved in any unnecessary school activities. Try to find free periods, bunking periods, or uh, periods where you can revise or solve problems. Many students just take a sheet of questions and solve it sitting on the backbench. Always try to uh, study in such a way where you are not only preparing for JEE but also preparing for boards at the same time, because theory is same. Just sometime you are solving maybe for boards, sometime you are solving for JEE preparation. Keep the board preparation 20% time wise maximum, I'm saying, and JEE wise keep it 80%. And do not study the same chapter separately. At once only continue that chapter for boards and JEE. Okay, for boards perspective, it is mainly derivations, formulas, and definitions, and give reasons and previous year questions. But for JEE, it's more application point. So you follow these things, you will definitely get it, and make more time by giving up your luxuries, waking up early, sleeping little late, and finding some small intervals of time. And joining an online class helps because you do not waste time, traveling up and down from your coaching. Yeah. Okay. All right. Thank you. Thank you that I'm looking 1 by cos C. Yeah. I know what it is, and I'm a physics maths teacher. Thank you. Okay. Yeah, you can definitely join Gokul, and it would be a very good thing if you join, because you also have your YouTube support classes, but that system will build in, test series will be there, assignments will be there, regular mentorship is there. Somebody is always pushing, and you are missing something if you don't attend. In YouTube, there is no commitment, right? So it's always better. Okay, right? Hey, Siri, such a waste, da. See, Siri is telling something. Ma. Okay, bro. Let's go ahead. So, imagine I give you a question, let's say like this. And let's say every part over here is some kind of a resistor. This is a resistor. It could be a capacitor also, guys. The methods are the same. So don't expect separate theory for it. Okay. Every part is a resistor over here. And we have to figure out what is the equivalent resistance between the ends. What is the equivalent resistance between the ends? Okay. So let's try it out. As you can see, 100% I can figure out there is some kind of line of symmetry over here. If I draw a line, yes, there is a line symmetry. And on that line symmetry, I can see a junction over here. I can definitely see a junction over here. And what did I say? The rule was whenever you see a junction, split it across the line of symmetry. Okay, let's do the same thing over here. So the moment I take that junction and split it across the line of symmetry, this is what I will get. This is what I will get. K, something like this, maybe. I've split it across the line of symmetry. Just check this out. This junction, split it across the line of symmetry. Took. That's it. Everybody gets this till this point over here. Now it is solvable, guys. I mean, like, see what we can do. These two resistors are in series. So it will be R plus R, which is 2R. That is in parallel with this. So if you combine this resistance along with this resistance, R1, R2 divided by R1 plus R2. So it will be 2R divided by 3. So all of them I can get rid of, and I can just write down one single resistance over here, which is now going to be 2R divided by 3. That 2R by 3 with this R and this R. Okay, I hope you got it. RR was 2R. These two are in parallel, so I use the parallel formula. Now this 2R by 3, this R and this R, all of them are in series. So let's see what it will be, this all things. So R plus 2R by 3 plus R. So that will be 2R common, 1 plus 1 by 3. Yeah, 2R, R plus R is 2R. So 2R plus 2R by 3. So that will be 2R 1 plus 1 by 3, that is nothing but 4 by 3, which is 8R divided by 3. That is the top part. Same thing I can do for the bottom part. That is just 2R because two resistors are in series. Now they both are in parallel. So therefore the equivalent resistance will be R1 multiplied by R2, which is 8R by 3 by R1 plus R2. So 2R plus 8R divided by 3. That's all. So 1R will be remaining. 2 8s are 16. So 16 by 3, of course, divided by 3 2s are 6. 6 plus 8 is 14. So 14 by 3. So 3 3 cancels. 16 by 14 times of R divisible by 2. So 8R divided by 7. So 8R by 7 is the answer. Yeah. Sir, if the resistance are no, it is basically, yeah, it is going to be 8R divided by 7. 8R divided by 7. Clear? Everyone till this point? Absolutely. Amazing, amazing, guys. So this is done. This is done. Okay, let's see some more questions coming up on your screen. Here it is. The effective resistance between A and B, if the resistance of each resistor is R, will be how much? Okay, as I can see, clearly there is a line of symmetry over here. Definitely there is a line of symmetry over here. And whatever is on the left side is on the right side. And I can see some devices connected instead of a junction. So I can get rid of this and I can get rid of this. So if I can get rid of them, how will they look? Well, like this, I believe. Yeah, this is how they will look. Okay, perfect. Now, next important thing, let me start reducing the circuit one by one. So as you can see, these two resistors are in series. So it will be 2R. These two are also in series. So that will be also 2R. And that is also in series. So that is 2R. 2R, 2R, 2R in parallel. So if you combine all of them, together, the equivalent will be 2R by 3 because they are in parallel combination. Now that 2R by 3 parallel combination is in series with these two. So therefore, the equivalent resistance will be this R plus this 2R by 3 plus that particular R. So 2R, R plus R is 2R plus 2R by 3. 3 2s are 6. So 6R plus 2R by 3. So it will be nothing but 8R divided by 3. So 8R divided by 3, which is nothing but option A. That is the correct answer. Okay, so step by step we have gone. So first we saw the line of symmetry. We saw there were two devices on the line of symmetry, completely waste. That's the rule. So forgot those devices. Then we saw they are in series, and their combination is in parallel. That parallel combination is in series with these two, one after the other. So just simple series circuit or parallel circuit. That's what the rule is, guys. Okay, always you will see this. Whenever line of symmetry is there, such that it is perpendicular, you will always find either devices or junction. You ignore the device or split the junction, it will become a simple series or parallel circuit. That's the rule. Very good. Excellent. Now, one of the most tricky questions is of the cube. Okay, one of the most tricky questions is of the cube. Clear? Very good. All right, everyone. How do we solve this question of the cube? There could be many cases, like you have to find equivalent resistance between these points here or these points here. Every problem has its own challenges. I'm just showing you one of the cube problems. Okay, maybe some other time we can take some other variation of the cube. So right now we have to find equivalent resistance between A and C, guys. Now that is the tricky part because it is a three-dimensional figure And now the moment you have three-dimensional figure, you have to think of three-dimensional symmetry. First of all, ignore that battery. I mean, that battery has no role to play here. It's just showing the 2 points across which you want to find the resistance. That is A and C. A and C, if you how many of you are able to visualize it now? There is a plane symmetry here. This is the plane of symmetry, and we have to find the resistance between this point and this point. You can see I can also join a line between them, and you can also see that this plane of symmetry is basically perpendicular. Can you see that? It is basically perpendicular over here. Can you see that, my dear warriors? How many of you are able to visualize it? It is definitely going to be perpendicular. Correct? Able to visualize it now? Yeah? Okay. Like this also you can get symmetry. But remember that plane of symmetry always has to be perpendicular to the points across which you want to find the capacitance or resistance. That is the trick. Then you should ignore the points on the plane or line of symmetry. Which components are there? I can already find them. Between B and E, forget it. These points are at the same potential. Even points D and E are at the same potential. So forget BE and DG. They are all at the same potential. Between B and D, there is nothing connecting. Between E and G, also nothing connecting. If there was something, I would forget that also. But right now, there is nothing. So I will not forget anything else. So let me redraw the diagram. This is very, very interesting. Okay. Battery not needed anyways. What else not needed? This particular thing, right? This between B and E and between D and G. Oh, now, sir, it looks little bit better for some reason. I don't know. It's looking much, much better. So between the points A and C, we have to find it. I think so. I mean, just look at it, guys. Already I'm seeing it. Observe this carefully. There is a resistor here and here. These two resistors together, R plus R, each side is 2 ohms. So R plus R, that means 2 plus 2, which is 4 ohms. This and this side is also 2 ohms each. So 2 plus 2 is 4 ohms. So they both are in parallel with each other. So this entire upper part of the cube is parallel. So 4 and 4 means 4 by 2, which is 2 ohms. So this entire part is 2 ohms. Everybody can see that? Same logic if I use, observe, this particular part is again 2 plus 2, which is 4 ohms. This part, series resistance. Can you see that? This particular part is series resistance. So again 4 ohms, and they both are in parallel. So that is 2 ohms again. But that 2 ohms is in series with this and this. Okay, but before that, let me do one thing. Let me simplify it and show it to you. What exactly I mean. Can get rid of these things over here. No longer needed. No longer need this also. So we have obviously this resistance here and this resistance here, 2 ohms and 2 ohms. And then we also have on the top over here one of the 2 ohms, and over here also another 2 ohms. That is what it is. So this entire part was 2 ohms. That's what I've written. And this entire part below was also 2 ohms. That's what I've written. This side here and this side here are still remaining. So keep those 2 ohms as it is untouched. Now this is straightforward, guys. I mean, you can clearly see that these three resistors are in series. So 2 plus 2 plus 2, which is 6 ohms. 6 and 2 are in parallel. So the R equivalent will be R1 R2 divided by R1 plus R2. So 6 2s are 12, 6 plus 2 is 8. So therefore, equivalent resistance will be divided by 4, that is 3, divided by 4, that is 2. So 3 by 2 ohms or 1.5 ohms. That is the answer. Yeah, perfecto. Some of you got it. Some of you now understanding it. Oh, this is how the cube questions are. It's not very lengthy also, guys. I mean, just step by step. So first step, like I have been saying, identify the points across which you want to find it. Try to draw a perpendicular. The moment you draw a perpendicular, all the points are at the same voltage. If there is a junction, split it. If there is a device, ignore it. So I can see two sides already of the cube being ignored. And now it is a simple series and parallel. This is series, they two are in parallel. This is series, they two are in parallel. And then, reduce the circuit and keep on reducing it till you get the final answer. Is that absolutely clear, my dear warriors? Loved it? Enjoying it? Okay. Sir, this is so cool. Tell me more about it. Well, guess what? There is something which is related to kind of symmetry, but even better than that, and that is Wheatstone's arrangement. So it goes something like this, where imagine you have okay, you have a circuit like this. You have a circuit like this, and let's say this resistance is R1, this resistance is R2. It could be capacitance also, by the way, R3, and this is, let's say, R4. And you connect any device in between, doesn't really matter. If you see such an arrangement, it is called as a Wheatstone's bridge. Even if it is a capacitor, even if it is a resistor, doesn't matter. But the Wheatstone is said to be balanced. The Wheatstone's bridge is balanced. It is said to be balanced if R1 by R2, this side by this side, this side by this side, R3 by R4, they are equal, then this device can be completely ignored. Then it can be completely ignored. If there is a voltmeter or ammeter, the current or the voltage shown will be zero. Nothing will flow through it. That is called as a Wheatstone's bridge. That is called as a Wheatstone's bridge. Everyone? Yeah, till this point, absolutely clear, my dear warriors? Okay. Once you do that, you will notice these two are in series. So as soon as you see that R1 and R2 are going to be in series, and the same thing about R3 and R4 are going to be in series, but their combination, this and this series combination, are side by side. Current will split up over here. Whatever current comes will partially go here and partially go here. So it is parallel. So they both are in parallel combination, which can be now easily solved for any kind of question. Easily you can solve it. Very straightforward. It is also applicable for capacitors. Okay. Also applicable for capacitors. Also applicable for capacitors. So in case of capacitors, if you replace this with capacitors, it will be like C1 by C2 will be C3 by C4. This is the balancing condition. This is the balancing condition. When it is balanced, so no current will flow in this part of the circuit. Clear? Okay. This could be anything, voltmeter, galvanometer, ammeter, resistor, anything will not show any deflection. But sometimes the Wheatstone might not be in its regular form. It might be in its irregular form also, like this. Maybe you have one resistance here, another resistance here, another resistance here, maybe a resistance here, resistance here, resistance here, like this, and maybe something like this. Two, four, eight, one, two, four, 4, 8, 16, 2, 3, 5, 7. This kind of circuit is there and you want to solve this. Okay, let me tell you, this is also a Wheatstone, but in a slightly extended form, not so easy looking form. See, when it is a simple Wheatstone, you just take this ratio and this ratio to be equal. If it is equal, then whatever is there here is ignored. But here, as you can see, there is one branch here, another branch here, and another branch here. If the resistors are in the same ratio, then whatever is connecting between them can be ignored. As you can see over here, 2 is to 4 is to 8 is equal to 1 is to 2 is to 1 is to 2 is to 4, which is also equal to 4 is to 8 is to 16. So that means what I can do over here, where is it? That means I can completely ignore this, ignore this, ignore this, and ignore this. So the branches which I'm talking about are over here. This is one branch, this is another branch, and this is another branch. So in each branch, the resistors should be in the same ratio, just like over here. In this branch and in this branch, the ratio of the resistors or capacitors is same. Then you can apply same way, even if there are 5, 6, 700 resistors also, as long as they are in the same ratio, you can ignore it. So the moment you ignore it, it will look something like this. It will look something like this. Not there, not there, not there, there. Okay. So like this, like this. Yeah. This is how it will be. Now this is a simple series and parallel circuit. You can easily convert it into a simple circuit. Maybe you can just say there is one resistor here, one resistor here, and then one resistor here. And then finally, it will be just a single resistance. Yeah, because as you can see over here, 2, 4, and 8 all are in series. So 8 plus 2, 10, 10 plus 4, 14. Okay, 1 plus 2, 3, 3 plus 4 is 7, and 4, 8, and 16. 16 plus 4, 20, 20 plus 8, 28. Now this can be easily solved. Understood, guys? Yep. Everyone understood how to solve this? Yeah, it is not that difficult after this, because you just have to do 1 by 14 plus 1 by 7 plus 1 by 28. LCM is nothing but, this is nothing but 1 by R equivalent. LCM is 28. This will be 2 times, this will be 4 times, this will be 1 time. So 2 plus 4, 6, 6 plus 1, 7. So 7 by 28, which is nothing but 1 by 4 actually. So R equivalent is nothing but 4 ohms. So that is the answer, 4 ohms. Yeah. Cool. Everyone understood? Yes. I'm so glad, Anugna. I learned physics from your classes. Also joined the Vedantu main online course. I got a seat in Hyderabad JNTU. Got top one college in Telangana. Warrior Pandu. I am so glad, Anugna. I'm so happy that you came back to tell this, and many students keep coming in the chats, in the lives, and keeps telling this. I'm so happy for you. Excited for your number one college journey in Telangana. I'm pretty sure you are going to be a great human and a great engineer. all the very best. Enjoy your first year and rock it till the fourth year of your college. Okay. Hope to see you after 4 years too. And anytime you guys come down to Bangalore, please say hello. I would be very excited to meet all of you. Yeah, great. If you have got 550 marks in NEET in regular tests at VLC, is it good? Uh, it depends on whether that particular test was hard or easy. Assuming that the test level was same as NEET 2025, 550 is a good score. Okay, so 550 means you will get a government seat. But I don't know what the level of paper was, so I cannot really comment because every paper is made differently every single time, so we can't really say. Okay, cool. Shall we go ahead, my dear warriors, now? Yeah, Wheatstone is done. Okay. Now, let's see whether you can solve this question within a second or two. Can you find the value of the current in the circuit given below? Potential at A is equal to potential at O. Okay. Actually, uh, this is a kind of Wheatstone. If it is told A and B's potentials are equal, what does it mean? It just means it's a balanced Wheatstone. See, this data, what does this data tell you? That means it is nothing but balanced Wheatstone. If it is balanced Wheatstone, that means what? 10 by 20, R1 by R2 is R3 by R4. That means R by 40. So what will R be? Obviously 20 ohms. And if that is also the case, this is completely useless. That resistance is useless. So if that resistance is useless, might as well not show it. Why do I have to show it? Just forget it. This is completely useless. And this resistance, we just got it. How much? We just got it as 20 ohms because it is in balanced condition. Now it is solvable. As you can see, these two are in series, so 30 ohms. These two are in series, so 60 ohms. Their entire thing is in parallel, so I can find the equivalent resistance. So 30 multiplied by 60 divided by 30 plus 60, so 3 6 are 18, so 1800. 30 plus 60, it is 90. 0 cancels. 180 by 90, 18 by 9 is 2, so 20. So 20 ohms is the equivalent resistance, but the question is on current. It is voltage by resistance. Voltage is 40, resistance is 20, so current will be 2 amperes. So that is the answer, 2 amperes, which is option number A. So very unique question which was asked. Very, very unique question. So they didn't tell it is a Wheatstone, but they gave it in a different way. That listen, A and B's voltage is same. I saw it is like Wheatstone. So if voltages are same, no current will flow through it. That means the resistors are in simple ratio. This one, this one, this one, this one. So I first found that resistance because then I can find the equivalent resistance, and from equivalent I can find how much current is flowing in the circuit. Got it? Lovely question, my dear warriors. Awesome. Let's see another amazing question on your screen. The current in the given circuit will be. Now, initially, this question looks like, okay, you might have to use KVL, KCL, some complex circuit. But trust me, this is actually nothing but a simple Wheatstone's bridge. I'll tell you how. Just look at it properly. This is 40 volts here. The current will come here and it is going into two branches. The current will come here and it is going into two branches, one here and one here. Okay. This is 4 ohms. This is 4 ohms. This is also 4 ohms. This 4 ohms and this 4 ohms, they are connected with 2 ohms. Oh, it's connected with this 2 ohms. And this point and this point, 4 ohms, which are then connected to the negative terminal like this. 4 ohms and 4 ohms like this. It is connected now to the negative terminal. Just check if you are able to see how this circuit is exactly this circuit. Can you see that? If you want, I'll mark the points. This point is this point. Oh, sorry. It is this point over. This point over here, and this point is this point over here. Okay. This particular point is this particular point over here. Yeah. And this point over here is this point over here. Now you can see the similarities. The current is coming into this, splitting it into two 4 ohms. The 4 ohms are connected by 2 ohms. That 2 ohm is also connected by two 4 ohms at this point. The 2 ohms is also connected by two 4 ohms at this point, which is connected to the negative terminal. Now it is basically a simple circuit where I can completely ignore this. And once I ignore this, I mean, that's it, guys. On the top, here you have one resistance, here you have one resistance. Okay, that's it. I have just converted this into a simpler circuit. 4 and 4 is basically 8 ohms. This 4 and 4 is also 8 ohms. And this battery is there, which is of 40 volts. So further reducing it to a simple circuit, both these 8 ohms are in parallel. So 4 ohms and just one single battery of 40 volts. So what will be the current? Voltage by resistance, which is 10 amperes. Excuse me. Yeah, 10 amperes. Option A is the correct answer. So sometimes it is in the disguised form. Okay, sometimes it is in the disguised form. So you need to be little careful about it. Okay, cool, guys. Loved the question? Perfect. Let's do another question, which is very, very nice. Okay, all these are fun to do. I'm pretty sure you are solving this and having fun. A wire of resistance R is bent into a triangular pyramid. Wow, as shown. This is a three-dimensional structure. This point is out of the plane, but in two-dimensional board, it can't be seen as a 3D. So just imagine this to be in 3 dimension. Okay. Each segment having same length, the resistance between A and B is how much? The value of N. I think there is some missing part in the question, if I'm not wrong. Maybe the resistance between them is NR or R by N. One of them will be there. I'm not really sure. For just solving the question, I'll solve it, then we'll see the answer. Okay. Something is there over here which is not printed. It's okay. The wire of resistance R is bent into a triangular pyramid. Each of these resistances are R. This is R, this is R, this is R, this is R, this is R. A wire of... Oh. No. Sorry. Each of them is not going to be R. That wire is bent into a pyramid. That means you take that wire, break it down into 6 small resistances. So each one of them is technically R by how much? 1, 2, 3, 4, 5, 6. R by 6. Oh, that is the trick. A lot of students will miss it. R by 6. Just reading it again and again, and it struck me suddenly. It is R by 6, guys. Read it. Wire of that resistance is bent into the pyramid. That means you break it down into 6 parts, and that's how you make that pyramid. Interesting? Loved it? Okay. Now, the resistance between point A and B. I already start seeing some kind of symmetry over here. As you can see, this particular symmetry. Yep. And I already can see there is one device which is on the line of symmetry. That is this one. That means it can be completely ignored. Whenever you see a line of symmetry, any device on that line of symmetry can be ignored. Okay, let me redraw that circuit now. Okay, let me redraw it for all of you. It can be ignored. Okay, boss, this is gone. Even this is gone. Now it looks like a slightly better circuit the moment you ignore that particular part over here. And how does it look like? Observe one by one. Okay, this and this are in series. So R by 6 plus R by 6 is 2 times R by 6, which is R by 3. Same story repeated here. That is also R by 3. But this one is R by 6. Oh, now we have three resistors in parallel. So if you have to find equivalent resistance, R equivalent will be 1 by R1 plus 1 by R2 plus 1 by R3. Oh, sorry, that is R by 6. So it will be 3 plus 3 plus 6, whole thing divided by R. That's nothing but 12 by R, but that is 1 by R equivalent. So therefore, R equivalent will be R by 12. I am guessing the question over here was, then the equivalent resistance between them is R by N. Then what is the value of N? So as you can see, the value of N is 12. Yes, that is the question. So the question was, I just guessed it now. It was R by N. So that was the misprint. So first I saw there is a line of symmetry. On that there is a device and it has same voltage, so I can ignore it. Now these two are in series, these two are in series, and these are three branches in between which are in parallel. So use the parallel formula, easily you will get the answer, which is 12. So R by 12 was the answer. So the required answer was number 12. Loving it, guys. These are the kind of questions you will get in current electricity and it will be fun. Yes or no? It will be fun. Very good. Amazing. We'll be solving more questions. Don't worry, more question solving series will come. But for now, let's go through the theory. Let's go through the concepts. Let's go from ground zero to high level. Okay. Loving it. Now comes the final part. Oh, by the way, we'll have a separate lecture for just voltmeter, ammeter, that meter bridge and power. Okay, so we'll have a separate class for that. So for now, today, we are doing till RC circuits, combination of resistors, everything resistor, capacitor will be done by today's lecture. And current electricity is a huge unit, heavy weightage also. So many questions you will find it. Yeah, in every competitive exam, current electricity is high weightage. RC circuit. So now we are not talking about RC discharging and charging. That is a deleted syllabus as of now. But long time ago there used to be RC charging as a function of time, discharging, time constant, all those things. Right now it is not there in the syllabus. But anyways, there are questions on the steady state. That means once it is charged or just when the switch is connected, then what happens? See guys, there is a very unique thing about capacitor which you should know. When you take a capacitor, the wires or the battery might have some resistance. Okay. Let's say this is EMF, this is the resistance, this is the capacitance. The charge on the capacitor, usually when you just connect this kind of a circuit, maybe there was a switch which was open and you just closed that switch. The charge in that circuit usually grows like this. C into E is the EMF. Is this constant, mathematical constant? 1 minus small e, that is that mathematical constant, minus time divided by resistance into capacitance. That's how it grows. So this is how the growth of charge is when the capacitor is getting charged. And if you put some special values, it becomes even more evident. Like for example, when the time is 0, if you put the value of time as 0, e raised to 0 is 1, 1 minus 1 is 0, so the charge on the capacitor will also be 0. That is initially. But when time becomes very, very large, you will notice t will become infinity. E raised to negative infinity is 1 by e raised to infinity. E raised to minus infinity is 1 by e raised to infinity. 1 by a very large number is as good as saying 0. So this term will vanish. So it will just become CE. So the final charge will be C. This is called as your steady state. This is called as your steady state. This is very, very important. This is what happens when you start charging a capacitor. This function you get it via integration and Kirchhoff's laws. Let's not break our head over it. For now, just accept this formula. Next important thing is, if you look at the current, right? Current is actually not zero. Current is actually the other way around. If you even try to find the current, by the way, okay, if you try to find the current, then you will find one very interesting thing. Initially, that particular current, initially, okay, charge might be zero, but it starts charging, right? So current will start coming. That current comes out as E by R initially, and finally the current becomes zero. It makes sense. When you just connect a capacitor in a circuit, current will start flowing. That's why it becomes charged. So there was no charge initially. And finally, when it is completely charged, then the current stops flowing because it is charged. It is steady state. No longer charge required. It has accumulated the charge. It will stop the flow of the current. So capacitor will block that current eventually. Okay. Right? Okay. See, one thing, Hemant. Last year, when we did road series, we did one shot long marathon. Now, this year, we are doing short classes. Instead of doing 6 hours, maybe 1.5 hour, 2 hours classes, but dividing the chapter into multiple classes is just a manner in which we are teaching. Number one. Number two, the reason why we are doing it is because of your stamina only and also our stamina. Once in a while is fine, but when you do it continuously, you also lose interest after 5 hours. Okay, what is sir teaching? Oh, what is happening? 4 hours. You lose focus. So we don't want that. Rather, we want it to be consistent. And when we take big classes, then the next time that chapter comes is after so many days, maybe a week. Now, almost in a week, you are seeing two classes of 12th standard, two classes of 11th standard for each subject. So that consistency, that habit building, and when you have smaller chunks, it is easy to absorb. So it's just a manner in which you are absorbing things. Otherwise, both are good. Cool. All right. All right. Fair enough. Similarly, if you go the reverse way, where a capacitor is already charged, and you are trying to discharge it via a resistor. So there was a switch which is now closed. The original charge was Q, and now you are trying to discharge it. Eventually, the charge will start going down. Then that charge as a function of time is that original charge into E raised to minus T divided by RC. This is how the function of the charge is. So if by chance you put the value of time as 0, that means initially. So T0, E raised to 0 is 1. So you will obviously see the initial charge as capital Q, which is initial. But if you put the value of time as infinity, then e raised to negative infinity is 1 by e raised to infinity, which is a very large number in the denominator, which means it will become 0. So after a long time, it will get discharged. So this is final steady state. If you ask me the current, well, finally the current will be 0 again over here, but initially the current will be there, and you can figure it out. It is not that difficult. Okay, it will be nothing but Q divided by RC. That is what it will be. Q divided by RC. How you can get it? Just take the derivative of this. dQ by dt is current. So then you will get the answer. Q by RC. Okay, that is how it is. Anyways, having said this, this is not there in the syllabus, but I'm just giving you that extra theory just in case maybe suddenly tomorrow they change the syllabus, God knows. Now, what I want from this entire slide is only this part, which is what happens when the capacitor is just connected or versus in steady state. So, if you take a capacitor, and let's say it is just connected, it is just connected, the switch is closed. Okay, then this capacitor, as you can see over here, it behaves as if there is no capacitance only, because the current in the circuit is E by R. E by R. So if there was a wire here, so current will be E by R. So initially, it behaves as if that capacitor has just vanished for that particular moment. So it behaves like a wire when it is just connected in the circuit. Very, very important. So whenever you see a capacitor, remove it, just connect a wire if it is just connected in the circuit initially. Okay, this is at t is equal to 0. But after a long time in the circuit, that means you have reached a steady state. So after a long time of connecting it in the circuit, then you can see what is happening. There is no current in the circuit. As if it has blocked it, that means it is open. So it behaves like an open circuit. So it behaves like an open circuit. Very, very important, guys. Very, very important. When it is just connected, it behaves like a wire. When it is there for a long time, it behaves like a wire. Just to give you a simple example, just imagine that we had a circuit which is like this, a resistor here, a capacitor here, and maybe a resistor here like this, and this is connected to a battery here. Let's say this is R, this is also R, this is C. Maybe the switch was over here. This is that switch. So when you just connect versus a long time, how will it behave? So when you just connect this switch, when this is just connected, what did I say? When it is just connected, wherever there is a capacitor, forget that there is a capacitor and just replace it with a simple wire. Replace it with a simple wire. That is how it looks like when it is just connected. I gave you the theory right over here. So now this looks like an easy problem to me. These two resistors are in parallel. So R equivalent will be R by 2 since they are in parallel. So now we can find out the current in the circuit. It will be E divided by R by 2, which is 2E divided by R. So that will be the current which will be flowing in that circuit. Very straightforward. Understood how to solve it? When it is just connected in the circuit, this is the current that will flow. But after a long time, but if you ask me what will happen after a long time, then if you are leaving it for a long time, then I just told you the capacitor behaves like an open circuit. So just forget that there was a capacitor, it is open. So the moment it is open, the current in this part will be 0. So all the current which has to flow will just go like this, like this, like this. Only through this resistor, it will bypass it completely and it will come over here. And this current, of course, will be just E by R. So it will completely ignore this branch. It is open. It cannot go through that. So it will bypass it and it will come like this. This is how it behaves after a long time versus initially. Okay, that is this concept of connecting a capacitor in steady state versus initial conditions. How many of you are clear? Let me know quickly in the chat box. Thumbs up. Yeah. And please, after the lectures, please solve a lot of PYQs. Lots means lots, especially from current electricity. This is a big chapter. You will find many PYQs also. It doesn't matter from which competitive exam, just pick up and keep solving. You will find always some good questions. Okay, nowadays you should not think about this exam or that exam. Gone are those days. Okay, perfect. Let's solve some questions coming up on your screen. Here it is. At steady state, the charge on the capacitor is how much? At steady state, what is the charge on the capacitor? Interesting. First of all, because it is steady state, I know one thing. This particular word is very important. Steady state. The capacitor behaves like an open circuit. So it behaves like an open circuit. So no current in the capacitor. No current in the capacitor. So completely ignore it. Just pretend as if it is not there. Just pretend as if it is not even there. Now, if at all, think about it. If you wanted how much charge is stored on that capacitor, okay? If I somehow figure out how much voltage drop is there over here, I can figure out that charge, because that charge will be capacitance multiplied by voltage drop. Capacitance is 8 micro, voltage drop I do not know. Okay. So somehow if I know the voltage drop, my job is done. How do I find the voltage drop? Sorry. Yeah. How do I find the voltage drop? I'll tell you what, this voltage drop can be found easily because this is series circuit. We can find the current, we can find the voltage drop very easily. Like so, how much will be the current? Current will be the voltage divided by the total resistance, which is 10 plus 15, which is 5 by 25, which is 1 by 5 of an ampere. Is that right? Current is voltage by resistance. Total resistance of the circuit is series. That means 10 plus 15. So how much will that voltage drop be? Current into resistance. Current is 1 by 5. Resistance is 10. So it will be 2 amperes. Sorry, 2 volts. It will be nothing but 2 volts. Use this data. Use this data over here. The voltage is 2. 8 to the 16. So 16 microcoulomb. So 16 means option number A, which is correct. That's how you solve it. So these kind of questions do come in the exam. Got it? Everyone? Perfecto, guys? Cool. Okay. Let's do another unique question, which is going to come up on your screen. Yeah, this one. Let's see if you guys can do this. An electrical circuit is drawn below the amount of charge which is stored in the capacitor. Again, something like that. Amount of charge stored in the capacitor. Again, I can see that this capacitor, because it is charged, it can be ignored. So capacitor in steady state is basically like open. The current in that part will be 0. So ignore that part and I will redraw it. Okay. So ignore this. If there is no current flowing in the capacitor, obviously there will be no current even flowing in this resistor. So completely useless, waste. So let's just ignore that. Okay. Now this looks like an easy circuit to me. I mean, what do I even have to do in this circuit? You might ask. Okay. Some current will definitely flow in this circuit like this. Same current will flow. If you ask me how much current, it will be the voltage by total resistance. So voltage is 10, total resistance is 4 plus 6. Oh my god, that is 10 by 10, which is 1 ampere. So 1 ampere of current is flowing, but what do I do with it, you might ask? Okay, we'll come back now. If it is an open circuit, okay, this particular part, if I want to find the charge on this, somehow, if I can figure out how much voltage drop is there, my job is done. Because the charge will be again capacitance multiplied by voltage drop. But I'll tell you what, capacitance is 10 micro. This particular resistance, since it has no current, there is no voltage only across it. Yeah, there is 0 volts because the current over here is 0. Oh my gosh. So what are you trying to say, sir? What I'm trying to say over here is that voltage drop across this capacitor is the same across this entire part or this entire branch, because this is having no contribution at all. So it is the same as saying this is also going to be delta V. Oh, really? This entire thing will be delta V? Yes, because this plus this will be the total voltage. And this has no contribution. So 5 plus 0 is 5. So x plus 0 is x. So this has no role to play. So whatever voltage is across capacitor is across this, is across this, is across this. And I can find the voltage across R3. Just think about it. If somebody asks me what is the voltage across R3, I'll quickly say, yes, that voltage will be current multiplied by resistance. Current is 1, resistance is 6. So it will be 6 volts. Perfect. So I'll multiply it by 6. So that will be 60 microcoulomb. That is the answer, which is C for your Captain Shreyas. Perfect. That is the correct answer. So these kind of tricky questions can be also asked. Everyone? Everyone? Okay. Awesome. 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 Very nice. I hope this is absolutely clear. Perfecto. How about this particular question? This is also very nice question. Okay. Again, capacitors and resistors combined. You might be like, sir, this is Wheatstone. Okay, wait a minute. Check properly whether it is Wheatstone or not. Okay, I'm going like this. One branch here, one branch here. 4:2, 3:9. My God, it is not a Wheatstone. So a lot of people will be like, sir, this capacitor can be ignored. Both the potentials are same. Answer will be 0 volts, but 0 is not even in the answer. Okay, 0 wrong. It is not a balanced Wheatstone. Oh my gosh, what to do? Don't worry. It's capacitor, man. And it is in steady state. So ignore that capacitor first of all. So in steady state, so in steady state, a capacitor behaves just like a wire. That is what my theory was. I told you. Capacitor behaves like a, oops, sorry, what am I saying? Wire. Open circuit. My bad. Capacitor behaves like an open circuit. No current will flow. Current in that will be 0. Okay. So what can I do? I can forget it. So let me just forget it and see what do I really get over here. Get rid of this. Okay. Now, in order to find the charge stored in the capacitor, obviously over here, in order to find the charge which is stored on the capacitor, somehow I should know how much is the voltage difference between these 2 points. Again, the same concept. Q is equal to capacitance multiplied by voltage difference. Capacitance is 6 micro. So if I can just figure out how much is the voltage difference, this point and this point, not so straightforward. I'll have to play around with this circuit a lot. How much is the voltage at this point? How do I know? Okay, I have an idea. Let's first find out what is the equivalent resistance of the circuit. Okay, this circuit, this circuit, as you can see, it's made of these 2 resistors in series, which is 6 ohms, and these 2 resistors again in series, which is of 12 ohms. They both are in parallel, of course. So equivalent resistance will be R1 R2 divided by R1 plus R2. Is that right? Okay, everyone. So 72 divided by 18, which is basically 4 ohms. So we can immediately figure out how much is this current. Voltage divided by resistance. So it will be 3 amperes. So 3 amperes is the total current which will go into that circuit. But it will not be distributed equally. Keep that in mind. This is 6, this is 12. So unequal distribution of currents will be there. So maybe some current will go over here. Let's say I call it I1. Some current will go over here. Let's say I call it I2. How much will be I1 and I2? Not that difficult. This resistance is 12 ohms and voltage is 12 volts. How much will this current be? Current will be voltage by resistance. Voltage difference by resistance. Voltage difference is 12. Resistance is 12. Oh, it will be 1 ampere. Same thing, current to voltage difference. Voltage difference is 12. Resistance is 6, which is 2 amperes. And kind of makes sense. 1 ampere and 2 amperes makes up 3 amperes. So this current is 1 ampere. This current is 2 amperes. In parallel, the voltages are same. So the concept which I've used over here, potential difference is same in parallel circuits. So these two were obviously in parallel. So whether you take these two or this, 12 volts, 12 volts, 12 volts, that is the voltage. So once I get the currents, I think now we can figure it out. See, if I assume this particular point to be 0 volts, chumma, this will be then 12 volts. If that is 12, even this will be 12. So how much will this point be? I am having a current of 1 ampere in the direction of the flow. There will be a drop. So it will be 12 minus IR, Kirchhoff's laws sign convention, I into R. Voltage drop will be there. So it will be nothing but 9 volts, this point. Same thing over here, 2 amperes is flowing. This particular point will have a voltage of 12 minus I into R, 2 into 4, which is 8. 12 minus 8 is 4 volts. Oh, so this is 9 volts, this is 4 volts. Now we can find how much is this delta V. So that delta V will be obviously 9 minus 4, which is 5 volts. Once we get that, now we can put it over here. So charge will be capacitance into voltage. So which is 5 volts, which we just got it over here. So 6 5s are 30. So 30 micro coulomb will be the answer. I think they have messed up the thing, but yeah, that should be the answer over here. Everyone clear about this? How we solved it? Yeah. 5 volts. Yep. Cool. I think, oh, they have asked energy stored in the circuit. My bad. Not the charge. So sorry, guys. Energy they have asked. So energy will be half CV square I can use. So half capacitance. Capacitance is 6 micro into voltage. Voltage is 5 square. Correct? So yes, 6 by 2 is 3. So 3 micro multiplied by 25. So that will be 75 microjoules. 75 is B option. Let's figure it out. Yes, it is correct. 75 microjoules. If charge was asked, then the answer will be 30 microjoules. Micro coulomb. My bad. Yeah, understood, guys, how to solve these kind of questions. Very nice, sweet, simple questions are there in current electricity. Once you get the flow of it, that's it. You will keep doing more such questions easily. So I've kept one homework question for all of you. Okay, please solve it. It's a nice question where I think Wheatstone's bridge might be there. I'm just chumma giving you a hint. Okay, solve this. Answer and the solution is there on the next slide. Okay, you can take a screenshot of it. I want everybody posting the answer in the comment section. Next lecture, we want to see who and all are doing it. Even if you're watching it recorded, please post it. Even after 2 months, 1 month, doesn't matter. Build that consistency. That's what these lecture series are meant to do. Okay, PDF will be attached in the description box as well as in the comment section. Okay, so check it out after a day, you will find it. I hope you enjoyed today's class. Smash that like button and hit the subscribe button in case you have forgotten. This was your captain Shreyas, your physics master teacher, and I'll see you next lecture.